So say you have N MOSFET. Okay, I draw on the top here. You have N MOSFET. This is N plus source. And then here you have your N plus drain. And then here you have your gate. And then here you have your body, and the body is P-type. Okay. And then this is your substrate. The same thing, I just draw it up to leave enough space in the bottom. So what actually happens is that you have N-type here, and you have N-type here, and you have P-type. So you actually have a NPN region. So this is the N region, this is the P region, and N region. So the N MOSFET, you can see here, this is the N MOSFET. It's really a cross between a MOS capacitor and a NPN transistor. So this NPN transistor and this MOS capacitor, there is cross. This cross produces the MOSFET action. It's a cross between a capacitor and the NPN transistor. So for the N, this N and the P, okay, you can actually draw an energy diagram, to show what happens. So initially we assume, okay, we don't apply any voltage here, we don't apply any voltage here, we don't apply any voltage here, we don't apply any voltage. All the terminals are free, set free, no voltage applied, So in that case, if you look here, here and here, you have a, and then we also want to give a direction. So we can call this as X direction. And we can call this Y direction. X and Y, okay? So these are two axes. So as you go along the X direction, you see, as you go along this direction, you see N, then you see a P, then you see N. Correct? And you haven't applied any voltage initially. You have no voltage here, no voltage here, no voltage here, no voltage. Everything is just in equilibrium. Nothing is applied. And all you see is N, P, and N. So the Fermi energy level that we discussed earlier will be just a flat one line all through. So you can draw the Fermi energy level from here to here. So this will be the EF, the Fermi energy level, all the way from here to here. We haven't applied, so it's all in equilibrium. And because this is the N type, so this Fermi energy level will be closer to the conduction band, isn't it? This is N type. So you will have your conduction band here, in this region. And this is the P type, so the Fermi energy level will be closer to the valence band. So you put your valence band close to valence band here, all the way up to here. And then this is the same doping level, so the Fermi level here will be closer to the conduction band. So you draw another line here. Okay. So now you have to make a band gap. Okay. Say the gap is this one, 1.1 electron volts. Okay. And then you have to make the same gap here, 1.1 electron volts, and make the same gap here. This is a bit large. Make it a bit closer. This amount here. The same amount here. Okay. So this is your how your energy band will look like, you know. This is exactly like an NP junction here and a PN junction here. Just two PN junctions in equilibrium. Okay, and this is your N side. You have your, you can draw all these ions here. Okay, and then you can draw your acceptor ions here because it's P type. And then you draw your donor ions here. This is N type here. And then you have your electrons here. Here is depletion region, so no electrons. Then you have a holes here. Depletion region, so no holes. Then here you draw your electrons here. Depletion region, no holes. No electrons here, electrons here, 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 here. And this is your phi bi. Remember, this is your phi bi. Q phi bi, the energy. Again, this is your Q phi bi, your energy. Q phi bi, built-in potential. So, one PN junction here, one PN junction. This PN junction going from N to P, this is going from P to N. Exactly based on what we did last time.
So Q phi taken off from EF, so it's the Q phi.
Q phi built in.
Is it taken from the P and from EF?
Yeah, the height, this is from the P, this is from the N, this is from the P. This is the P region from P going down to N, it's the same as this.
Okay, so you take one.
Okay. Okay. This one, basically the same. So this is going in the X direction. So you have two junctions. One is N plus P, other P to N plus. And those two junctions, like your BJT or your diode, this is one junction here, one junction here. That's it. Nothing special. And as you can see, this is the barrier here. See, so electrons here, you have electrons here, lot of electrons here, lot of electrons here, but they cannot go, because of the barrier, they cannot go. So then this is the X direction. Then you also have a diagram in the Y direction. In the Y direction, you have oxide here. Okay. This is a N plus, and this is P. So you go from N plus to P. You have another PN, but unfortunately, you have oxide in between. So how to draw the diagram? Bit complicated. See, if you have PN, then you can just draw, connect. But in this case, you have oxide in between. How to draw? The easiest way to draw that is to first draw the PN junction and then cut it into two pieces, separate them. Okay? Have you seen magic before? Magic? How many people have seen magic? Have you seen magic? What's magic? That you have the one guy who goes into the box, and then some guy has a saw, and cuts the box into half, and then puts it down, and then hands are moving, legs are moving. Use the same technique to draw your diagram going from the gate to the substrate. So you first draw your PN junction, then put it in a box, cut it with the saw, remove the box, then you'll get your energy diagram from gate through body to the substrate. Okay. So what you do here? So here you see you go from here to here. It's basically you'll end up something like this. This is the y direction. Okay, I'm drawing here in the y direction. Okay, this is going this way. This way. You have your gate here. So you'll have your gate here. Okay, and then you will have your oxide here. Oxide here. And then you will have your substrate here. So how to draw it, So what you can do is that you can first draw a p-n junction and separate it, or if you're confident, you can draw in one stroke. Okay. So here you see, this is in equilibrium because you haven't applied any voltage here. So everything is in equilibrium here also. So you can first draw your Fermi energy level like this. EF, you can say Y because the Fermi energy level I'm showing for the Y direction. You can call this X, I'm showing the Fermi energy level going this direction. Okay? This is going this direction. Okay? The X direction is going into the board, This is the X direction. Sometimes can be confusing, So you have this is the X direction, and this is this way, Y direction. Okay. So here, this is your N plus, so it's N type. So your Fermi energy level will be closer to the. And then, as it happens in a p-n junction diode, it will just go up slightly here, because the charges will move away and take equal amount, the same amount here, and then you will have your another band going this way. So you can label here. This is your E, C in the drain. This is your E, V in the drain. Okay, and this is your E, V in the source, and this is your E, V in the source. Okay. This is your E, C in the gate. This is your E, V in the gate. Okay. So in the gate, this is N-type dope. That means you have donor ions. So you can put your donor ions here. Okay, and you can put your electrons here, the ones that are fully covered by the holes, by the positive ion, and here of course they are not there, exactly like the p-n junction. And then you go to your substrate, which is p-type. That means the Fermi level will be closer to the valence band. Okay. So you draw like this. So this is going to be your E, V in the substrate. Okay. So you will have your negative ions here. Your negative ions here, negative ions here. And take the same gap, put it here. This will be your E, C in the substrate. So this gap here, between here to here, is 1.1 electron volt. Okay. And then this one, okay, this one is about, from here to here is about 3.3 electron volts. And then you go down here in the oxide, this is between here and here, is about 4.8 electron volts. So the total is 9.2, So from here to here, it's 9.2 electron volts. These are all negative ions, so it looks too small. The negative, these are negative ions. Let me just try to improve the diagram a little bit. Negative ion, all of them are negative ions. and then for each negative ion you have a hole. So you have a hole here, hole here, hole here, hole here, hole here, hole here, and no more hole here because those have moved from the junction. This is one straight line because it is in equilibrium. And if you remember, there was a line goes through the middle of the energy band, which is called EI. So you can always draw the EI if you want. Goes through the middle. This is EI. This is the energy, Fermi energy level if there was no doping at all. This will go through the middle, entirely through the middle. So you can also draw a line here through the middle. This is EI. And remember, you call phi FP, this is your phi FP. Phi FP. This is your phi FP. This gap from EI to EFY is your phi FP. This phi FP. This thing. Should I draw it again? It doesn't look too good, does it? Is it good enough or should I draw it again? Draw it again? Okay. Let's draw it again. So maybe try to draw it bigger now. Okay? Okay, draw it again. Okay. So we'll start again from x direction. For x direction, we'll go again C. So you first draw the Fermi energy level. Go straight, okay, between here and here. This is E, F, okay. And then you have your N-type material, so the conduction band will be closer to the Fermi level. So conduction will be top, so maybe I do the conduction band here. No? Yeah, the conduction band. And then I make a bigger gap this time. Put it here. This is E, F of the source. Sorry, E, C of the source. E, C of the source. This is E, V of the source. Okay. And similarly here, exactly the same gap here. This is your E, C of the drain. Exactly same distance here. E, V of the drain. Valence band of the drain, conduction band of the drain. This is the conduction band at the source, valence band at the source. Okay. And here you have N-type, you have donor ions. So you can, before you do that, you actually do the P-type. So P-type, you can draw your valence band, which will be closer to the Fermi level. So you can draw it somewhere here. Say. Okay. And then use the same gap, go all the way here up to here. And then now you have your barriers again. So you can draw your positive charge here, okay, positive charge here for the N region, and then your electrons here. Again here you can draw your positive charge, and you can draw your electrons here. For the P region, you can draw your negative charge here. And your corresponding holes here. Then you have your barrier here. Between here, you have phi built-in electron volts. Phi built-in electron volts. Is it better? Bit better. And you can put your intrinsic level at the midway. You see, midway between here is somewhere here. Midway. This is your EI, intrinsic. If it is not doped at all, this is going to be your Fermi energy level. Was going to be. So now you see, you have this barrier. This barrier here, this barrier here. Now I'm going to draw the y direction again. So this is the x direction. I'm going to draw the y direction. Okay. Y direction is the same. You have again a p-n junction, but there is a gap between them. Okay, there is a gap between them because of the oxide. So I can draw the oxide first. Because it's very large. Let me make it very large. There is a large gap between the conduction band and the valence band in oxide. You expect for any material which is a dielectric, the amount of energy required for electron to go to the conduction band will be high, isn't it? Because it doesn't conduct. A dielectric doesn't conduct current. Why? Because it is very difficult to excite an electron into the conduction band. That's why your energy gap is large. So this is 1.1 electron volts. This is 1.1 electron volts, 1.1 electron volts. But this one is not so size here, it's 9.2 electron volts. Okay? So you can draw the other side, n side here. Because it is not connected to any voltage, it is in equilibrium, so the Fermi level will be constant this way. This is the Fermi level in the x direction. This is the E, F in the y direction. It's balanced, everything in equilibrium. Okay. So this is the end region, so the conduction band will be closer to the Fermi level. So you can draw like this here. And this region will be closer to the valence band. So you can draw like this here. This is your E, C in the gate. This is your E, V in the gate. This is your E, C in the substrate. This is your E, V in the substrate. And then you can put your charges here. And you can put your charges here for the piece, for this P region, negative ions. Okay, and then you can put your electrons here, exactly like a p-n junction. See, exactly same, except that there is a gap here. this is 1.1 electron volt, and from here to here, this is a large gap. From here to here, all the way here, is 9.2 electron volts, of which this part is 3.3 electron volts. This part is 4.8 electron volts. Is this better? Okay. So this is the picture when you don't do anything. This is the y direction. And you can also draw the intrinsic level here, like we draw the other case. This is your EI. This distance is your phi FP, that phi. Okay. So this is easier to understand. This is a bit more difficult because you have this oxide in between. So that's why I said what you do is that you remove the oxide, draw one for a p-n junction, then separate them, cut it out like the magician. Then you'll get your diagram for the oxide with the oxide. So this is your poly, N plus poly gate. This is your oxide. There's your p substrate. So how will you actually influence? How will you influence your operation? You have to lower this barrier. Okay. So once you apply a voltage, which I'm going to draw here. Okay. Once you apply a voltage, again you draw your transistor again. This time you are going to apply a voltage between the. So this is your body. This is your source. This is your drain. And this is your gate. So between the gate and source, I am going to apply voltage VGS. VGS, which is, as we said, greater than threshold voltage, greater than VPHN. And the body and the source will connect together. We will not have any body effect. So if you connect this, how much is VSB? If you make this connection, how much is VSB? Body and source connected, how much is VSB? Zero, isn't it? VSB is 0. So we don't use body effect. That's VSB 0. Okay. So this, all of this together can be connected to ground. Okay. So now what will happen? If you apply voltage VGS greater than VTHN, what will happen here? This Fermi level, we haven't applied any voltage here, so this will stay the same. You see. So what will happen is that this will stay the same. This is EF will stay the same. Okay. We again look at the energy levels. Okay. Your EC will remain the same. Okay. EC will remain the same here. Closer to the. Okay. It's the same gap. And then we draw this part, same gap. Okay. Same gap. here what will happen is that now, before it was very high, this will come down. This will come down. Same gap. This is what's going to happen. This has been lowered now because of the field effect. So now what will happen is that you will have again those ions here, and then you will have your negative ions here. And you will have some holes here. And then you have a lot of electrons here, because now, because the barrier has been reduced, the electrons can flow. So there will be electrons all over the place. Electron here, electron here, electron here, electron here. And there is no charge here, the negative charge here only, but there will be electrons from here will flow into the channel. There will be a lot of electrons here because the barrier has been reduced. So now you have channel here. You have channel. Okay. So now you have the channel. This is what's going on. If applied field greater than threshold voltage, this has gone down. You see, this has gone down. You see the Fermi level is actually closer to the conduction band here in the p-type material. So it has become almost n-type in the top here, and you have a lot of electrons all over there. So now the channel is on. So the MOSFET is on. But is it conducting current? Is there any current flowing from source to drain?
No.
Is there any current flowing?
No.
Any current flowing? You have turned it on, but is there current flowing? No current flowing, because you haven't applied a voltage between the drain and the source. I have applied a voltage to turn it on only, but I haven't applied a voltage for the flow of the current. Okay. So this diagram will change. Of course, I am not going to do this diagram to draw this again, but I only need to show this diagram to show you how the barrier is lowered. So when the barrier is lowered, actually this goes down like this, which I don't want to draw again. This will go again bend quite a little bit. It will all be bent. So this diagram in the x direction, this is what's going to happen. So have you understood this? Basically this and this, most important. Have you understood this and this? You have a barrier and you have a barrier reduced. Have you understood that? So this is the main principle, that you have a barrier and you reduce the barrier. So now you have formed the channel. Now how to flow the current? How to make the current flow? What do I have to do? What do you have to do? I have treated the channel, turned on the channel, now I have to flow the current. What do I have to do? Apply voltage between the source and drain. You agree? Apply voltage between the source and drain. So now I am going to apply voltage between drain and source and see what happens. So I am going to do it here. Can I erase this? Okay, I am going to do it here. So the channel is on, and then I am going to apply voltage between the drain and the source. So which voltage will be higher and which will be lower? Which voltage will be higher, drain or source, to make the current flow? This is higher, this is higher. We want to flow the current this way, flow the electron this way. So this is higher, this is higher. This is already connected to current. See, this is higher. Yes, you agree? already connected to ground. If you apply a positive voltage here, all electrons will flow this way. That's what we want to do. You know. So now we have turned it on and we want to make the current flow. So we draw another diagram here. This is your P plus body. This is the N plus source. This is your N plus drain. Okay. So this is your source. This is your body, which are connected together and connected to ground. And here is your gate. And between the gate and source, we applied a voltage, isn't it? VGS, VGS, which is greater than VTHN. In this case, VTHN is equal to VTH0, isn't it? Because the body and source are connected together, so VSB is 0. Because VSB is 0, VTHN is the same as VTHNO. Correct? Okay. And then we have also done one more thing here. We've taken the source and connected through a battery, another one to the drain, which we call VDS. Okay. So now we want to flow the current, so we have applied a voltage, and the channel is on all at the moment. This channel is on. There are electrons here, happy to move to the drain with the applied voltage. So what's going to happen now? So you have source here whose voltage is 0 volts, and drain here whose voltage is VDS. So where is the energy higher, here or here? Where is the energy higher? Is this part have higher energy or this part have higher energy?
The drain.
Higher energy. This is VDS. What is the energy here? What is the energy here? 0 volts, 0 electron volts, isn't it? What is the energy here? What is the energy here of electron? How much? What is the energy of electron here? This is plus VDS. You see plus. So what is the energy here? Come on, come on.
Negative.
Yes. How much?
VDS.
Minus VDS. Yes. Minus VDS electron volts. The energy here. So how are you going to draw it? Very simple. Now what you have to do is that this Fermi level here is at 0 electron volts, and here it must go down. Okay, so you must go down. So you draw like this, like this. This is your E, F in the source, and the drain, which is here, E, F in the drain. The difference will be VDS electron. Okay. So if you draw your lines here, you can go up to here. You can go up to here. Okay. Make a gap this much, whatever you want. Okay. And then here, make the same gap. This will be again N type, same diffusion. So you have a conduction band here. Make the same gap, and then it will go down like this. This is your EC in the source, EV in the source. This is your EC in the drain. This is your EV in the drain. You don't need to write all those charges all the time, but you can see the barrier is gone down like this. So all these electrons coming this way, they will fall down here like this, roll down here, they drift across this region, and go into the drain. Okay. So what is this case? This case VGS is greater than VTH and VDS is a small voltage. Which is less than VGS minus VTH. Less than. Okay, see how it's working then? You have this. When you don't have any voltage between drain and source, it's just flat here, nothing is going. But as soon as you apply voltage, you create a potential going down, you see, a rolling hill. So you can have electrons moving this way. Okay? Rolling down.
And what's wrong? Why don't you want VGH?
Because unless the configuration of the BJT is on off, but these are mainly used for amplification. You know that amplification doesn't go on.
Okay, yeah, right. You don't just want it to be on.
You see that from there, it's going to come back like you are, guarantee it. Yeah, because when you do amplification, that side there moves up and down, and that's how it increases your signal. Because as you can see, the more you move it down, the more electrons flow, so the higher your output signal. So when you've got a sine wave audio, you at your peaks, that's going to go up, and that drops this on the way down.